So welcome everybody. I'm very happy to see all friends around, and I don't have to make a big introduction. We have the opportunity to say a lot during this week. The only new thing is that slowly the constructions go on. So these buildings and another one, hopefully at some point will be provide office space for you to work when you come here. Of course, they were disturbed because in the beginning of the meeting, unfortunately, but it was a very hard day. But anyway, this goes on, and these are the good news. Otherwise, we had several meetings already. Everything was successful. And from your participation, I'm sure this will be a very successful meeting too. So.
Okay, so we can start the workshop. And the first speaker is Robert Brandenberger. And the title is Emergent Space-Time and Early Universe Cosmology from Matrix Theory. Please.
Can you hear me? My voice loud enough? Okay, so first of all, I would like to thank the organizers for inviting me to speak, to be here. I feel a little bit like an intruder because I don't come from your community of non-commutative geometry. I come from the community of cosmology. And in cosmology, I think we have a big problem these days. And I think you all in this community here, you can all help. So my talk is going to be divided into two parts. One is going to be something which I feel very confident about. And what I will try to argue in the first part of my talk is two things. First of all, is that inflation is not the only early universe scenario which is consistent with data. It is not the only one. So as a field theorist or as a quantum gravity expert, you do not need to try to force inflation into your theory. Absolutely not. And secondly, I think that there's a big problem in trying to use point particle effective field theory in cosmology. So I also feel very strongly that if we want to understand not only the early universe, but also the late universe, we have to go beyond point particle effective field theory. So these are points which I feel very strongly about and very confident about. So given what I just said, I should try to do something new. And so the second part of the talk is going to be my attempts to try to do something new. And I have to acknowledge that this is based on work that is done by a lot of you here, in particular by a lot of people who are connecting via Zoom. And I saw a couple of names from Professors Kawai, Tsuchiya, and Nishimura. So a lot of the work that I'll be presenting is based on their pioneering work and on your pioneering work. And since I'm not a string theorist and I'm not a formal field theorist, I could be making big mistakes. And maybe you can catch my big mistakes and help improve. So this is the menu for today. So let's see. Good. So you probably have all been told that the inflationary universe scenario is a current paradigm of early universe cosmology, and inflation is usually analyzed using an effective field theory framework. Now, we're warning, my critique is not so much a critique against inflation per se, but it is a critique against inflation using effective field theory, namely using general relativity coupled to point particle classical field theory, which is what is done. So anyway, I'm going to argue that there are conceptual problems using such a description, and these are not small problems. These are unitarity problems and violations of the second law of thermodynamics. So we better be consistent with unitarity, and we better be consistent with the second law of thermodynamics. Otherwise, we're doing something very wrong. So based on this, we need to look beyond effective point particle field theory if we want to understand cosmology. And so then, this will be my attempt. Okay, so my critique. So 20 years ago, Jérôme Martin and myself discussed this space-time diagram. And so here the vertical axis is time, the horizontal axis is spatial coordinate. And this space-time diagram corresponds to inflationary cosmology. So in inflation, there's a Big Bang singularity, and then there's a finite duration period where space expands exponentially. So now there are several length scales which I draw. First of all, the horizon, which is the forward light cone from some point on the initial Cauchy surface. And during the phase when space expands exponentially, the horizon expands exponentially. And therefore, it becomes exponentially larger than the second length scale, which is the Hubble radius, which is the inverse expansion rate. Hubble radius, inverse expansion rate. Cosmologists often call this horizon, and that causes lots of confusion. The third length scale is a length scale that corresponds to inhomogeneities which we observe in the universe. Distribution of galaxies and isotopies in the microwave background. So these are small amplitude fluctuations superimposed on a homogeneous anisotropic background. And this indicates the length scale of such an inhomogeneity. And during the phase of inflation, the length scale expands exponentially. And in particular, if this phase of inflation lasts long enough, this length scale starts out smaller than the Hubble radius, which allows a locally causal generation mechanism for fluctuation. If you have questions about that, I can come back to that at the end. Now, in terms of your interests, there's another length scale, which is the non-commutativity scale, or the string length, or the Planck length. And I think you will all agree with me that we cannot use point particle commutative effective field theory on these length scales. But this is what inflation does. And so this is a problem for inflation, the trans-Planckian problem. So if inflation lasts long enough, there's a breakdown of the methods that cosmologists use. And it's a breakdown that affects predictions of inflation. Okay. Good. So now, based on this space-time diagram, 3 years ago now, Vafa and Bedroya postulated a censorship conjecture, which they called trans-Planckian censorship conjecture. And that says that no cosmology consistent with ultraviolet physics can have the property that trans-Planckian modes, initial trans-Planckian modes, ever become bigger than the Hubble radius. So you see, this is what's happening here in this diagram. Initial trans-Planckian modes become bigger than the Hubble radius. So the trans-Planckian censorship conjecture says that this is prohibited. Mathematically, this means the following. If you start at some initial time with a Planck length, and you expand to a later time, t sub r, any later time, you have to remain smaller than the Hubble radius at this later time. So this is the trans-Planckian censorship conjecture. And now I'm going to give you 3 justifications for this trans-Planckian censorship conjecture. The first is an analogy with black hole physics, in analogy with Penrose's cosmic censorship hypothesis. So here you have a space-time diagram of a black hole with charge smaller than the mass. So this is the bad singularity. This is the horizon. And the observer who's far outside of the horizon is shielded from the bad stuff that happens at the singularity by this horizon. However, Einstein's effective field theory allows for solutions where the charge is greater than the mass. And for those solutions, the poor observer far away from the black hole is not shielded from the bad stuff that happens at the singularity. For example, non-unitarity. And therefore, Penrose made the following conjecture. He said that even if the effective field theory allows for such pathological solutions, the theory that completes the effective field theory should prohibit these pathological solutions. So this is Penrose's black hole censorship hypothesis. Now let's translate this hypothesis from black hole physics to cosmology using this translation scheme. So position space becomes momentum space. The singularity becomes the space of trans-Planckian modes. So the things we don't understand becomes the things we don't understand. And the black hole horizon is replaced by the Hubble horizon. So under this translation scheme, Penrose, paraphrased, says that an observer measuring only super horizon modes must be shielded from trans-Planckian modes. So that's the first justification for the TCC. Okay. So now the second justification is a unitarity problem, which was actually raised a long time ago in a paper by Nathan Weiss in 1985. And this issue was brought up more recently by Kotler and Strominger. So this is a basic unitarity problem of point particle effective field theory in an expanding universe. So what do we do in point particle effective field theory? We take all fields, we expand in Fourier modes, and we quantize each Fourier mode as a harmonic oscillator. That's what I mean by effective field theory. Okay. Now, in order to avoid the Planckian catastrophe, we need an ultraviolet cutoff. And this ultraviolet cutoff is at a fixed physical length scale, not at a fixed co-moving length scale. But in an expanding universe, the modes which you quantize are co-moving modes. So therefore, to maintain the fixed ultraviolet cutoff in an expanded universe, you have to continuously create modes. This is extreme non-unitarity. And if you demand that the classical region be insensitive to the bad stuff, to the non-unitarity, then you get precisely the trans-Planckian censorship conjecture. Okay, a side remark, which a lot of you have actually already realized in publications. So the cosmological constant problem, the famous cosmological constant problem, comes from using effective field theory. Because what we do is exactly we quantize harmonic oscillators. Each harmonic oscillator has a ground state energy. Ground state energy adds up to infinity, or cut off to the fourth. Now, if we have a quantization scheme that never quantizes any harmonic oscillators, the cosmological constant problem takes a very different light. And I'll come back to that at the end, because I'll claim that the model that I'll present has no cosmological constant problem. Okay. Now, the third justification for the trans-Planckian censorship conjecture is a bit more fuzzy, not in the sense of your fuzziness, but in the sense of a little bit uncertain. This is an entanglement entropy argument. Now, in black hole physics, people use a lot entanglement between sub and super horizon modes. Well, let's do the same thing in cosmology. We have entanglement between sub and super Hubble modes. And in an inflationary universe, the phase space of super Hubble modes is increasing, and therefore the entanglement entropy is increasing. The entanglement entropy density is increasing. So if we demand that the entanglement entropy density remains smaller than the post-inflationary thermal entropy, which we want to produce our cosmology, then we get exactly the trans-Planckian censorship conjecture. So, okay. So you see, this problem is specific to inflation. It's specific to accelerating backgrounds. The other ones were more general. Okay, so now I have to show you that we do not need inflation. Sorry, I skipped something. If you want inflation, and if you want inflation to be consistent with the trans-Planckian censorship conjecture, what do you need to do? Okay, so this is my space-time diagram of inflation. So the inflationary phase, post-inflation. This is a Planck length, or your non-commutativity length scale. This is the Hubble horizon. And this is the length scale of fluctuations which we observe today. Now, I drew this space-time diagram as being marginally consistent with the trans-Planckian censorship conjecture because the Planck length at the beginning of inflation grows to exactly the Hubble length at the end of inflation. Inflation cannot last any longer than I drew. But if inflation is to be successful, then our current Hubble radius, scales where we make observations, has to emerge from inside of the Hubble radius at the beginning of inflation. Otherwise, we don't have a causal generation mechanism. So the TCC sets an upper bound on the duration of inflation. Inflation being successful for cosmology sets a lower bound on the duration of inflation. And whether these are consistent depends on where the Hubble radius is located relative to the Planck length. The higher the energy scale of inflation, the closer the Hubble radius is to this Planck length. So therefore, you will see that if you want inflation to be consistent with the trans-Planckian censorship conjecture and successful, then you will have to satisfy these two criteria, TCC and our current Hubble radius emerging from inside of the Hubble radius at the beginning of inflation. And that sets an upper bound on the energy scale of inflation, which is about 5 orders of magnitude less than the canonical scale. And if you have inflation with such a low energy scale, you will get absolutely no primordial gravitational waves. So whenever you hear people telling you that the spectrum of primordial gravitational waves is a telltale signal of inflation, I'm sure many of you have heard this statement. This statement is absolutely, absolutely wrong. Because, first of all, inflation consistent with the trans-Planckian censorship conjecture predicts essentially vanishing primordial gravitational waves. And secondly, because the alternatives to inflation predict gravitational waves. So the statement that you've often heard is wrong on two sides. Okay. It also, the TCC also implies that dark energy cannot be a bare cosmological constant. Okay. So now, what are the other scenarios of our universe cosmology which can do better than inflation, or which at least can explain the data as well as inflation? So this is the data that I want to focus on. And this is the angular power spectrum of microwave anisotropies. So here you have an angular scale. And this is the amplitude of anisotropies in the cosmic microwave background on this angular scale. And I'm sure almost all of you have seen this plot before. Is that correct? Who has not seen this? Okay, one person has not seen. Anyway, but this is the angular scale. This is the amplitude of anisotropies on this scale. Okay. Well, it's multiple moment.
Okay.
Okay, so now the data, I show you the data from the WMAP satellite, is these black dots with some statistical uncertainties, which are now much smaller, and some systematic uncertainty here. And now this red curve, it is a 6-parameter fit. 6 parameters of late-time cosmology have been fit to get optimal agreement with this curve. And now the first people to have calculated this red curve are Zeldovich and Zunyaev and Peebles and Yu in 1969, 1970, 10 years before inflation. So whenever someone says that this curve was first predicted by inflation, absolutely wrong. Okay, this, to demonstrate this, here is a poor representation of a figure in the Zeldovich-Zunyaev paper. So here you have time. Here you have co-moving spatial coordinates. So these are coordinates which are constant as space expands. So fluctuations have constant co-moving length. Okay, this is the Hubble radius. This is the time of recombination when the microwave background is produced. Now, what Zeldovich and Zunyaev argued is the following. Given a spectrum of small amplitude inhomogeneities on these scales coming from the primordial universe, then these fluctuations will be frozen in until the length scale becomes smaller than the Hubble radius. And I can explain this to you in detail later on. So you have a set of standing waves, and one by one, they enter the Hubble radius and they start to oscillate. So this mode has had no time to oscillate before recombination. We catch the wave at maximal extent. This wave has done 5/4 of an oscillation. We catch it at minimal amplitude, maximal velocity. This will give maximal microwave anisotropy. This will give minimal microwave anisotropy. So this picture here explains these acoustic oscillations in the microwave background. And all you need to fit the exact form is 6 late-time cosmology parameters. Okay. So here's a statement. Given a scale invariant power spectrum of fluctuations on scales which were superhorizon before equal matter and radiation, this is known to give a good power spectrum of galaxies, good distribution of galaxies. It predicts acoustic oscillations in the microwave background, and it also predicts the famous baryon acoustic oscillations in the matter power spectrum. This is Zeldovich and Zuniayev, 1970, and parallel Peebles and Yu, also 1970, 10 years before inflation. Okay, so now the question is, how do we realize this? This is the question. And indeed, inflation is the first scenario with which these criteria could all be realized. So this is my space-time diagram of inflation. So, okay, I think I skipped the slide. Okay. These are my criteria for successful early universe cosmology. First of all, to produce the isotopy, the near isotopy of the microwave background, the horizon has to be much, much bigger than the Hubble radius. First criterion. The second criterion, if you want a causal generation mechanism of fluctuations, then scales that we observe today have to originate inside the Hubble radius at early times. And then we need to generate scale invariant spectrum of curvature perturbation. These are the three requirements, and I will give you three scenarios which satisfy them. First of all, inflation. The horizon is exponentially larger than the Hubble radius. You produce isotopy. Scales of cosmological interest today originate inside the Hubble radius. You can have a causal generation mechanism. And then the constant energy density during inflation produces the scale invariance of the perturbations. So scenario one, inflation does satisfy the three criteria. But here you have another scenario, a bounce in cosmology. So Harald has worked on this. So here we postulate, and again, we have to go beyond effective field theory to get that. We postulate that the radius of the universe, the scale factor, starts out in a contracting phase. Then there's some new physics which gives you a bounce, and then you end up in standard Big Bang expansion. This is what the Hubble radius does. So time, space, co-moving distance. Time runs from -infinity to +infinity. The horizon is infinite. So criterion one satisfied, Hubble radius smaller than a horizon. Here you see what fluctuation modes do. Sufficiently far back in the past, they are sub-Hubble, causal generation mechanism possible. And then there are bouncing cosmologies for which you can create scale invariant spectra. And I can talk about that later. So this is the second scenario. Now, the scenario that will be important for the second half of my talk is what I call the emergent scenario, where we assume that the universe starts in a quasi-static phase, or in a phase which, from the point of view of general relativity, will be quasi-static. For this community, you should view it as a non-commutative phase, a phase in which there is no classical space-time. And then there's a phase transition to standard Big Bang expansion. So this is what I'm assuming. This is the resulting space-time diagram, time, space. This is the emergent phase. This is the transition time, the phase transition time, standard Big Bang-like expansion. Time runs from -infinity to +infinity, so horizon is infinite. Hubble radius is smaller than the horizon, but the Hubble radius in the emergent phase is infinite. And so therefore, all fluctuation modes start out sub-Hubble, causal generation mechanism possible. And what I will show you is that if you start with thermal fluctuations in this emergent phase, not quantum fluctuations, thermal fluctuations in this emergent phase, and if these thermal fluctuations have holographic scaling, then you get perturbations which are completely consistent with our observations. We get scale invariant spectra of cosmological perturbations and gravitational waves, and we get a prediction that the tilt of the tensor modes of the gravitational waves is slightly blue, not slightly red, as inflation predicts. So there are three scenarios of early universe cosmology which are consistent with the data, not just one. And in order to have a good scenario of early universe cosmology, we have to go beyond effective field theory. Oops, I went too fast again. Okay, so a provocative slide. Bouncing cosmologies are trivially consistent with the Transplanckian censorship conjecture, provided that the energy scale of the bounce is lower than the Planck scale. For people in this audience, replace energy scale at the bounce with your non-commutative energy scale. Emergent cosmologies are also consistent with the TCC, with the same condition. It is only the poor inflationary scenario which has trouble with the Transplanckian censorship conjecture. However, all early universe scenarios need to go beyond point particle effective field theory. Okay, so I was speaking quite loud because I'm quite confident about the statements that I made, even though some of them are controversial. But now I will tune down and speak more softly, because now I'm less confident about what I'm going to talk about. So obviously, since I gave this message, I have to try to do something new. How much time do I have? Okay, good. So now I will try to show you a way to get emergent metric space-time from matrix theory and an emergent early universe cosmology with fluctuations which are completely consistent with observations. And with no cosmological constant. Okay, so obviously I could be completely wrong. There could be fatal mistakes in what I'm presenting, and you might be able to catch some of these fatal mistakes. But so I'm attempting to do something. So please be a little bit patient. So my starting point is the BFSS matrix model. And I will take this BFSS matrix model in a high temperature state. So now you see my starting point is, for some people, it is rather conservative, because I'm not inventing a new matrix model. I'm taking this matrix model, which was proposed more than 25 years ago as a non-perturbative definition of stringy M theory. So there's no space. There are obviously no singularities. It is a quantum mechanical model of 10 n by n Hermitian matrices, and you take the limit where n goes to infinity. So this is the Lagrangian. Here you see 9 n by n Hermitian matrices. There is a potential term. There's a kinetic term. This looks like a covariant derivative. It is a partial derivative plus a commutator with a 10th matrix A0. And there's a coupling constant. These are n by n matrices, and we take n going to infinity in the 't Hooft sense. So this is the Lagrangian that I'm going to be working with. And I will consider this model in a high temperature state. And I will use results which were derived by many of you. For example, the result that at high temperature, the bosonic sector of the Euclidean BFSS model is well approximated by the bosonic sector of the Euclidean IKKT matrix model, in the sense that if we expand the matrices in Matsubara frequencies, that then it is the zero mode, the zero Matsubara mode that dominates the BFSS action. And the contributions of the zero modes, they have exactly the form of the IKKT action. You see here, the zero mode, there's no time dependence. The time dependencies are disappeared. Okay, so this is the IKKT action. Here we have no space and no time. All we have is the action and the partition function. And here I've added the fermions to make it supersymmetric. Although in our work, we have hardly used the fermions, and including the fermions is very important. Okay, so good. So now what we need to do is we need to try to get emergent time, emergent space, and an emergent metric, and an emergent cosmology out of this model. Okay, so what do we do? Again, we are not inventing anything new. You see, we follow the work that was done by the Japanese group, some of whom are online. So we can always diagonalize one of the matrices. We diagonalize A0, and we interpret the eigenvalues of A0 as our temporal eigenvalues. Okay. Now we use one result of numerical studies, and this is this fact that the expectation value of the trace of A0 square, 1 over n, scales as kappa n, kappa is some small constant, in the n going to infinity limit. Now, what does that mean for the diagonal elements? What does that mean for time? So the first thing it means is that the maximal value of time scales as square root of n, not n. Also, the eigenvalues are symmetric around 0. Symmetric around 0. Now, this also implies that the difference between temporal eigenvalues goes as 1 over square root of n, because the n temporal or 2n temporal eigenvalues, the maximum is square root of n. So what we get out of this in the n going to infinity limit, we are getting infinite continuous time. So that this is not new. Okay, so good. So now we will continue to work in this basis where A0 is diagonal. And now we look at the spatial matrix elements. So we take the AI's, expectation value of AI square, and we look at how these elements behave if we go away from the diagonal. The diagonal is A equals B. And okay, there are 3 features of these expectation values. So we can show analytically by looking at the partition function and using the Riemann-Lebesgue lemma that these elements decay when A minus B becomes bigger than n sub c, where n sub c scales as square root of n. This can be argued for analytically, just by looking at the action. What we have not got a handle on analytically is the fact that was numerically observed is that if you are within n sub c, then these elements are approximately constant. Okay, so good. So now we will again follow what was done by Professors Nishimura, Tsuchiya, and their collaborators, is we will try to get emergent space at a particular time. So our goal is to get emergent space at a particular time t. So a particular time t means somewhere a particular distance down the diagonal. So now we go the same distance down the diagonal for the spatial matrices, and we will look at a small n by small n subblock. And I want to get my space out of these subblocks. And again, we are not the first ones to do that. In fact, here you see 3 years ago, here in Corfu, Professor Nishimura explained that you can define extent of space parameters. So for each of the 9 spatial matrices, you can look at these subblocks, and you can look at this expectation value, and you can view it, you can interpret this as an extent of space parameter in direction I. And then what has been observed numerically is that in the thermal state, there's a spontaneous symmetry breaking. Only 3 of these extent of space parameters become large. The other 6 remain small, remain at the non-commutativity scale. Okay, so this has been observed numerically, and you can verify it using Gaussian expansion method techniques. And here are the references. Now, the physical reason why this happens, and this is a conjecture that I put forward to you, and I hope to make progress on this conjecture in this meeting. I think the reason for this symmetry breaking is the following. Strings arise in this matrix model as solitonic states, one-dimensional solitonic states. The solitonic states wind the whole space, in order for space to be able to expand, the solitons have to break. This only happens in 3 and not more large spatial dimensions, as Waffa and I argued back in 1989. And this is why the symmetry breaking pattern is exactly this. It's conjecture, and I would like to see progress on that. Okay, so now the proposal is the following. I will now define my co-moving spatial coordinate as the size of the subblock. So I'll define my n sub I as the size of the subblock of the ith matrix. And the length is the extent of space parameter. So the extent of space parameter is interpreted as giving the physical length from n equals 0 to n. So this is a physical length, which is a generalization of Nishimura's extent of space parameter. This is co-moving coordinate. If we have length, yeah. Okay, go back to this picture. So you see here we have a spatial matrix A sub I. This is a sub matrix at a particular time. N sub I is the length of that. Okay. No. What I'm using is I'm getting the expectation values of these matrices will give me space. And so what I'm looking at is I'm looking at the expectation values of these sub matrices as the size changes. And the size I interpret as co-moving coordinate, and the extent of space I interpret as physical length. Yes, because whenever in cosmology, you are free to choose whatever co-moving coordinates you want. Obviously, the form of the metric depends on what you choose as co-moving coordinates. But the curvature of the metric is invariant of how you choose the co-moving coordinate. Thanks for the question. Okay, so now you see that once you have the physical length of the curve and the co-moving coordinates, you can get the metric in this way. So this is a metric. It is the II component of the metric. And what you find using the properties of the expectation values is that these GIIs of n are independent of n for small n smaller than m sub c. So what we get is we get a metric whose diagonal elements in the 1, 2, 3 directions have this form. We use SO3 symmetry that gives us this metric, and this is a metric of a spatially flat 3-dimensional space. Okay, so we get emergent time, continuous, ranging from -infinity to +infinity, continuous space, infinite, in the end going to infinity limit because n sub c goes to infinity. We get an emergent spatial metric, which is spatially flat. We don't need inflation to make space flat. Spatial flatness emergent. I should actually mention that there's parallel work by Waffa and collaborators where they use topological arguments and they get similar results that we are getting here. Okay, so now in the last maybe 7 minutes, or maybe only 5 minutes, I will now turn to the cosmology. Okay, so first of all is that if you study classical solutions of the matrix equations, then again, this is work of the Japanese groups, we get that this A of t goes as t to the 1/2, like radiation. Now, the reason it doesn't go like t to the 2/3, like matter, is that we don't have the fermions included. So there's no sign of a cosmological constant. So this cosmology that emerges has no cosmological constant. And why should it? We never quantize a harmonic oscillator. So the cosmological constant problem has a very different light. Okay, so now the last thing I want to do is I want to get the fluctuations out of this model. So now we go back to the starting point, which was the BFSS matrix model, where there are the temperature corrections. There are the corrections which are suppressed by 1 over the temperature. Now, I will assume that the symmetry breaking this symmetry breaking that has been shown in the IKKT model, and it also holds in the BFSS matrix model. And what we've just this month have been able to show, and I should acknowledge the work of Sudha Brahma, who's connecting via Zoom from Edinburgh. To visa reasons, he's not able to be here. And Samuel Laliberté is a student of mine. So we've just been able to show that there is a phase transition also in the BFSS matrix model. So the SO9 symmetric state is not energetically preferred. We've not, with our tools, we've not been able to show that we get that the symmetry breaking is into SO3 cross SO6. But I have no doubt, based on my heuristic understanding why this symmetry breaking happens, I have no doubt that this symmetry breaking will also occur. Okay, so now we have a thermal system, so we have thermal fluctuations. And the thermal fluctuations are given by the partition function. So if you have the partition function of a thermal system, you can compute the energy density fluctuations and you can compute the pressure perturbations. The energy density perturbations give you the curvature fluctuations, which we observe today in a microwave background. And the anisotropic pressure perturbations give us the gravitational waves. So you see, with the action of the BFSS matrix model, taking into account the 1/T corrections, we have a possibility of computing observables. Okay. Good. So the way we do that is the following. So for each length scale, we want to compute the fluctuation. And at the end of the emergent phase, each length scale, one by one, becomes larger than the Hubble horizon. And so what we do is we compute the correlation functions in the emergent phase on all scales. And at the time that that particular scale becomes larger than the Hubble radius, we use the Einstein constraint equations to compute the induced curvature perturbations and induced gravitational waves. So these equations, which are here, are equations for the curvature perturbations and for the gravitational waves about a spatially homogeneous and isotropic metric. So these are simply the Einstein constraint equations here. Energy density fluctuations give us the curvature perturbations. Off-diagonal pressure perturbations give us the gravitational waves. I didn't write down that I is not equal to J. So this is a principle. Given the partition function, we compute these quantities, and then we use these equations to compute observables. So I hope I've stressed the method, and then I don't have to stress too much the actual calculations. So the power spectrum, which observers want, it is basically the Fourier mode of the curvature perturbation square times k cubed, dimensionless. It is given in terms of the energy density perturbation, specific heat capacity. The specific heat capacity is given in terms of the internal energy on a particular scale. The internal energy on that particular scale is given by the time derivative of the partition function on that particular scale. We have this, therefore we have this, therefore we can calculate this. So this is a method. Okay, specifically, I think I'll skip this side, I can come back to it. Based on these calculations, we find that we get a scale invariant spectrum of curvature perturbations with a Poisson contribution on ultraviolet scale. This is the new thing that didn't arise in our string gas cosmology toy model, which is specific to this BFSS matrix model. This scale invariant spectrum of curvature perturbation has exactly the same form as 10 years ago we got, 15 years ago we got in string gas cosmology. We also get a scale invariant spectrum of gravitational waves. And so the conclusion seems to be that this BFSS matrix model yields, taken in a high temperature state, yields emergent infinite space, emergent infinite time, an emergent spatially flat metric, and an expanding early universe phase with thermal fluctuations which lead to scale invariant curvature perturbations and gravitational waves, and there's no cosmological constant. And I just want to emphasize that the horizon problem is automatically solved. Okay, so I'm now almost out of time. I have 2 more minutes and I'm ready to conclude. So obviously there are lots of open problems and I would like to make progress on some of these open problems. So we need to understand, to include the effects of the fermions. We need to understand the phase transition between the emergent phase and the expanding phase better. That will then allow us to compute the spectral indices, not just the overall amplitude of the curvature perturbation. And it will also then allow us to address late-time cosmology. Okay, so there are lots of things, lots of work to do. Okay, so I have 2 concluding slides. One concluding slide is what I believe to be robust conclusions, robust messages. First of all, inflation is not the only scenario of early universe cosmology which is consistent with current data. In spite of what you'll hear in many astronomy talks, and unfortunately, in spite of what is written in introductory astronomy textbooks. Now, in light of the trans-Planckian censorship conjecture and other conceptual problems, swampland, effective field theory models of inflation are not viable. And if you want to understand the early universe and also the late universe, I think you have to go beyond point particle effective field theory. So I view this as the robust messages that I want to convey to you. Now, based on the last point, there was this attempt to do something new, to take the BFSS matrix model, since it's a proposed non-perturbative definition of superstring theory, and to try to obtain space-time and early universe cosmology. And I presented you our attempt, and it's an attempt. I'm proud of the attempt, but it may be wrong. So thanks for listening.
And George is the last, and then Joyce. Yes. Yes.
Participants in here too.
When you ask questions, wait for the microphone, not so much for the audience, local audience, but for the people in remote.
When you went from the BFSS to the IKKT, you retained the fermions, whereas the fermions would normally decouple at high temperature.
Yes.
I mean, you required the fermions for Nishimura et al.'s symmetry break in the IKKT.
That's right.
So,
yeah, I see your question. So you see here in this very recent work, we've gone back to the BFSS and we've used the fermions in the BFSS model to show that there is a phase transition.
it's a high temperature phase transition.
High temperature phase transition. So we've shown that the symmetric state does not minimize the free energy
at high temperature.
At high temperature.
And the fermions are essential for that.
Fermions are essential for that. In the same way that they were essential in the IKKT analysis. And we use the same Gaussian expansion method.
But the fermions should decouple at high temperature.
They contribute to the 1/T corrections.
Yes, they do, yes. And you're saying it's a one of them.
So you see, going back to the so if we want to stick completely to the BFSS matrix model description, I'm using the zero Matsubar modes of the BFSS model to obtain emergent space and time. And going through IKKT was just to make connection with the works that were already done. I think you want me to stay completely in BFSS. And the answer is yes, we can do this.
I'm not quite understanding how the fermions are playing that role, but I need to look at your paper, I suppose.
There is a whole body of work from the math side, starting from Gelfand-Naimark, going through Alain Kohn and recent also by Doppler, Fredenhagen and Roberts, okay, which really is quantum. You have algebras of observables in space around, and they try to see how the space-time as we know it, it is topology and differential structure can emerge from the spectrum of the C-star algebras. Here I don't see anything like that. So I don't understand the connect. Is this quantum or classical? I don't know. Okay. Or is it little quantum, little classical?
This is quantum.
Then,
we are
then
the
algebras of observables and what are the states?
We do not have algebra of observables.
Then you have no quantum mechanics.
So we are starting with a quantum. Okay, we have not discussed. We have not used algebra of observables.
But then you don't see anything. I mean, what if you don't have algebra of observables?
Okay,
you can't see anything. Okay?
I think we should talk about this. I think there is an answer to that question, but I do not know it right now.
Yeah, I can comment. The algebra of matrices is a crude approximation of some non-commutative algebra, which would describe a non-commutative space-time. So, of course, it's a very crude approximation, but if it's an algebra of operators, will be represented as matrices on a infinite matrices on a Hilbert space.
Just a last comment, going from matrices to the larger limit has been considered again from the point of view of C-star algebras and physics, I would say, by Araki Woods. Okay? And that depends sensitively on the way one takes the limit n going to infinity. You end up getting type 1, type 2, type 2.1, type 3.1. So here there is no such thing. It is very mysterious. Crude means, is it correct? I don't know. What is the topology? What are the open sets? What is the differential structure?
Okay, so we do. Okay. So the answer to your last point is we do not have a classical differential geometry yet out of this. So.
Okay, maybe my first difficulty is related to the previous. I have a difficulty to understand how you get the metric. I was thinking of metric, but I did not dare to go from matrix. Well, this is my first question. Maybe you can say a comment here.
Right. So this is the way that we are proposing to get the metric. So we have so first of all, you have to accept that I'm looking at subblocks of varying size, and the size of the subblock is my co-moving coordinate. So I don't just want to obtain an overall extent of space, but I want to obtain the continuous space. I go to capital N goes to infinity, and that means that the n sub c goes to infinity. And you see here, I'm getting the metric for all. This is a proposal to get the metric for all small n, smaller than n sub c. So what I start is with this definition of the physical length of a curve between n equals 0 and n. My co-moving coordinate n. And you see, this is a quantum object. And then this is the usual way of getting from, if you have the length and you have co-moving coordinates, this is how you get the metric.
Okay, so my second question is related to the future project that you mentioned about, let's say, dark energy, dark matter, and so on, which of course you did not tell us, but I'm sure you thought about that. Do you think that one has to violate these censorships that you mentioned in the beginning to get that?
No.
Without putting...
No, absolutely not. I think this will be completely consistent with a trans-Planckian censorship conjecture. This is an emergent cosmology, and there will never be any length scales that are relevant to observations which are smaller than the Planck length or the non-commutative scale.
So in this scenario, you think will be again dark energy, dark...
no, dark energy I cannot claim yet, but the cosmology that emerges will be an emergent cosmology which is completely consistent with the trans-Planckian censorship conjecture.
Okay.
I think we can thank again the speaker. I think your hope of being provocative to us has got a success. And I remind you that we have a lot of time for discussions and alternatively going to the beach or both of them. The next speaker is Efstratios Pateloudis, and the title is Studies of the D0 matrix model at low temperature. And you see my weapons.
Okay. Good to go. Okay. Okay. Hi, everybody. Let me start by thanking the organizers for giving me the opportunity to speak here in this very nice workshop organized here in Kerkira. So my talk, I'm going to discuss about the D0 brain matrix model, as Robert introduced in the beginning. And this is work which is based on these papers appeared and some work in progress. And my collaborators are listed here, specifically Spergen, Bodendorfer, Hanada, Rinaldi, Schaefer, Branas, and Watanabe. So we are also known as MCS-MC from Monte Carlo string M-theory collaboration. And the question I want to start with is why I'm interested in lower temperatures, and the answer is fairly simple. It is simple because low temperatures, at low temperatures, we have analytically known bulk duals, specifically gravity duals, as I'm going to discuss. And there are also some interesting physics happening that hopefully I will convince you that this is the case. So this is the plan of the talk. I'm going to discuss and to define the models. Then I'm going to discuss the relation with gravity and how holography works in these specific models. I'm going to discuss an interesting phase that we believe it exists in D0 brain matrix models, and this is the confinement phase. Then I'm going to use simulations of these models to test interesting physics at low temperatures. And specifically, I'm going to compare eternal energies of black hole-like geometries with these matrix models. And then finally, I'm going to discuss whether the gates symmetry is an important characteristic such that the idea of gates gravity duality works. So let me start by defining the model. As Robert introduced, I'm going to give a little bit more detail, so I'm going to back up a little bit. So the action I'm interested in is defined by these parameters, and I have listed all these the field contents in this color in these colors here. So I have 9 bosonic Hermitian matrices. I have 16 fermionic matrices. The covariant derivative acts on observables like this. And the important thing is that I have the 't Hooft coupling, which has dimension of energy cube. This makes the theory non-conformal. Actually, it turns out to be a matrix supersymmetric quantum mechanical model. So this model you can arrive at it as a dimensional reduction from different theories in different dimensionalities with different supersymmetries. And in the context of M theory, and specifically in 11-dimensional space-time, it has been studied by DeWitt, Hope, and Nicolai in '88 as a matrix regularization of the supermembrane. Of course, it was around even before the work of these people here, where other people were trying to understand supersymmetric matrix quantum mechanics. And 8 years after the work of DeWitt, Hope, and Nicolai, Banks, Fissler, Senke, and Susskind, they proposed this specific model here as a non-perturbative definition of M theory. And this one is, I think, is a standard procedure when somebody can compactify higher dimensional theories. For example, you can start with a 10-dimensional super Yang-Mills theory with one supersymmetry and compactify 9 of these dimensions, and you arrive in this, yes. At the same time, you can arrive at the same model by using a 4-dimensional super Yang-Mills theory with n = 4 supersymmetry. And after the work of BFSS, these people here, Itzhaki, Maldacena, Sonnenschein, and Yankelowitz, they proposed in terms of holography that this model should be dual to a black zero brane in a near 't Hooft limit. And I'm going to, of course, discuss the last 2 points here. So the generic idea is that the Gates gravity duality in string theory, maybe I guess most of you are familiar with, is that black p branes in certain superstring theories, they are dual to p + 1-dimensional UN super Yang-Mills theories, which contain DP branes and open strings. In this talk, I'm going to consider p = 0. So here I will have a black zero brane in type 2A string theory. And here I will have a 0 + 1-dimensional theory, which was the theory I showed before. Of course, there is a lot of work also for p = -1, which is the IKKT model, which many people present in the audience and online have been worked. But today I'm going to discuss the p = 0. So the idea of how holography works and the way, at least I understand it, I will present it quite intuitively, I think. So, because the 't Hooft coupling has dimensions of energy cubed, I can define and can introduce an effective dimensionless coupling by dividing with appropriate powers of energy. And the idea then is that if I have a matrix like this, which is n by n, diagonal elements correspond to positions and locations of these zero branes, and non-diagonal elements correspond to open strings stretching between these zero branes. And since I have 9 matrices, because there are 9 bosonic matrices, each matrix, it gives me information about 1 dimension. So if I have 9 of them, I have an information about how these zero branes are spread in this 9-dimensional space. And I remind you the Lagrangian, which is a term, interaction term like this, which is reminds somehow pi to the 4 theory, and the potential is of this form. So it is quite trivial to see that the solution of this is when all matrices are 0. And the question is, what does this correspond to the gravity side? Now, before I answer this question, I'm going to introduce a deformation of this model here, which is known as the BMN model by Bernstein, Maldacena, and Nastase. So basically, you have the axion of BFSS, and you add some more terms, which are listed here. So what you do is you add mass for the fermions and for the bosons and for the fermions. And at the same time, you are adding a Myers term, which is a cubic term of this form. So this mu here is a parameter which has different interpretation, but in this context, it is the mass of the fermions and the bosons. So the bosonic potential in this case takes this form here, and if I plot it schematically, it is of this form. So you see here that you have two different vacua of the theory. One is the trivial one when all matrices are 0, but you also have some SU2 vacua which correspond to fuzzy spheres. Now this results in an explicit breaking of the symmetries from SO9 to SO3 times SO6, which is quite clear from the indices which run here. And the fuzzy spheres, they live in the SO3 part of this space-time. But today, as interesting as they are, the fuzzy spheres themselves, and it is of much importance for this conference, unfortunately, I don't have enough data to say about those. So I'm going to focus on the trivial vacua. Yes. Yes, here the breaking is at the level of the axion. So it is, you can see here the way you introduce the mass terms for bosons. You have indices running from 1 to 3, and here from 4 to 9. So these capture the explicit breaking of the symmetries. Good. So let me now switch to the gravity interpretation. And the idea is that here from this effective coupling, if I fix lambda, the strong coupling regime at the level of the effective coupling corresponds to low energies. And at low energies, I have a solution of 10-dimensional Einstein's equations, which is called the black zero brane in type 2A supergravity. And this kind of geometry has this specific metric here. And of course, when somebody wants to study thermal physics, you have a horizon which is of this form. And thermal physics, you can also do thermodynamic analysis. So you can find the energy of this black zero brane and the entropy. And the idea now is that this kind of geometry corresponds to a very precise region in this phase diagram, which was given by Itzhaki, Maldacena, and Yankelowitz. So here on the y-axis, you have log n, which is, if you wish, the number of degrees of freedom or the number of d0 branes. And on the y-axis, you have log g effective, which is schematically log of the inverse energy. So the idea is that you can use certain restrictions coming from curvature of the horizon when you from the curvature of the S8 sphere here, you require that the curvature is small, such that you can use this geometry to describe the black zero brane classically, and also you require the dilaton on the horizon given by this expression here to be small. So when you do that, you can restrict your geometry to be valid into this black area. But the question is, what happens if I want to lower further down the temperatures or the energy? So you see here that if I go to lower energies, I'm expecting the theory to flow from this region here towards the right. So now I'm going to explain what is the interpretation and how this can be done intuitively. And to do this, I have to define, I have to take the usual definition of type 2A superstring theory, which is defined as M theory compactified on a circle S1. So this circle is related with the string coupling GS, and the later is also the dilaton, And the dilaton, I told you, that has a specific expression, goes like G effective with some power. And this G effective is lambda over energy cubed. So again, if I fix lambda and take the large and Hooft limit, what I require is to probe M theory. I have to go to very low energies, such that the radius of this circle starts opening up. So when this radius starts opening up, I cannot neglect it anymore. And therefore, I have to take into account the M theory picture and not the type 2A superstring theory. So schematically, pictorially, if you wish, the idea is that for high energies, I am in this area here. I start going to lower energies, which means that the radius of this compact circle starts growing. I am entering into M theory, and even if I go to even lower energies, I expect to flow to matrix black holes. But the idea, the warning here is that these two phases are not really well under control, and they are not really well understood until now. So now I'm going to switch to simulations to try to understand these problems. And for this, I'm going to use the BFSS or BMN models, the models I introduced before, and I'm going to put them on a supercomputer. I'm going to borrow techniques from lattice QCD, but here things are fairly easier because I have just one dimension to parameterize, which I may call time. And when I want to discuss thermal physics, I compactify this time with circumference given as inverse of temperature. The parameters that control the system is n, the matrix size. S is the lattice points, the points I'm parameterizing the circle, and temperature gives the circumference of this circle here. In the matrix model, this corresponds to this kind of picture, and the large n limit is taken by fixing lambda to 1, for example, and sending n to infinity. So again, by reminding you the interpretation of in terms of diagonal and non-diagonal elements, taking large n corresponds to building more and more space or information about how these D0 branes are spread on R9. And intuitively, this can be understood something like this. So the idea is that for finite n, my space-time will always be non-commutative because of the matrix characters, but I'm expecting in the large n limit, this non-commutativity to become smooth and sort of classical. So one more ingredient that I have to introduce to talk about the studies later is the Polyakov loop. So the Polyakov loop is defined as this. So the trace over the ordered exponential of the Gates field. And on the lattice, I can write it in terms of its phases, like exponentials to I theta j, where theta j runs from minus pi to pi. And whenever you have a restoration or breaking of the U1 symmetry, which is the center of UN or UN, I have a transition from confinement to deconfinement. And this kind of idea is well understood in the case of the usual ADS-CFT, which is CFT4, which we have the super Yang-Mills theory in 4 dimensions, and ADS5 process 5. So there has been some work done by several people in this context, and the idea is that whenever the Polyakov loop and the energy are of order of 0, you have confinement phase, and this confinement phase is interpreted as a graviton gas. On the other hand, whenever your energy is non-zero, and the Polyakov loop is around 1/2 or greater, then you have the deconfined phase, which corresponds to a phase where your bulk theory has black holes. And this, in fact, can be taken according to these people here. This can be taken as a definition. Whenever your Polyakov loop is 1/2, then you have necessarily black hole-like geometries. So the way we see this in simulations is the following. So here I have the Polyakov loop in y-axis, and I have the Monte Carlo time in x-axis. And here you see signals from a confined phase to a deconfined phase, which the Polyakov loop is around 1/2. And this corresponds to black hole-like geometries. While on the other hand, in the bottom, I have the inverse characteristic where I start from a deconfined phase and I flow into a confinement phase, where the Polyakov loop fluctuates around 0. And the idea now is that I have slightly a problem. The problem is that the gravity theory predicts always the confinement. You can see this by recalling the energy. And for non-zero temperature, the energy cannot be 0. So the idea is, so the question now I have to understand is how to understand the confined phase. So either something has to be wrong in this kind of idea, or we have to find something else to explain, some other physics. Before I go there, I have to convince you, or I have to show you that the confinement phase survives in the large n limit and in the continuum limit. So in other words, the gravity theory is classical, and I have to make sure that I get the same classical physics from the matrix model. So here in the left picture, I have large n extrapolation at fixed lattice sites and fixed temperature. So temperature is 0.2. I take the lattice site to be 8, and I'm doing some large n extrapolation indicated here. So for n equal 10, 12, 16, and I'm extrapolating to infinity. And here I'm plotting different observables. So with red is the energy, with green is the Polyakov loop here, and this blue line is the sum of the trace x squared, the normalized sum, which tells you that the trace x squared, the sum remains constant. But I want to bring your attention to the Polyakov loop, which goes to 0 when you take the large n limit. At the same time, I have to do the continuum extrapolation. And you see here I plot the same observables, but here are the lattice sites, and I'm simulating different lattices, and I am extrapolating to the continuum, and it is the energy in this case that flows to 0. So when I combine both these extrapolations, I have to choose whether I am in the deconfined phase or in the confined phase. So if I would be in the deconfined phase, the energy would be at 0.08 at t equals 0.2. So this means the energy could be around here. And the Polyakov loop would be around 0.5. So this means the Polyakov loop should be all the way up here. So from this, the only valid conclusion I can get is that I am in the confined phase, where the energy and the Polyakov loop, they are flowing to 0 respectively when I take large n and continuum extrapolations. Okay, so now how do I understand this? So to understand this, I have to build some motivation from, again, the conventional holography, where you have ADS5 crosses 5. And again, these people here, they try to construct the phase diagram of these theories. And you can, for example, start with the microcanonical ensemble when you fix the energy and you scan for different phases of your theory. So this means I'm fixing energies here. And you see that for very high energies, I just have one stable phase, which is a big ADS big black hole, which is filling this ADS 5. As I lower the energies, I have another phase accompanied with a transition here, which is unstable. It has a negative specific heat. It corresponds to a small Schwarzschild black hole, which is localized on S5, and it has negative specific heat. And when I lower even more the energies, I have another transition, and the idea is that this confinement phase, which is indicated here by this blue line, corresponds to graviton gas in 10-dimensional supergravity. So this is a very well understood example, and it is reviewed in these two papers. And now what I want to do is I want to play the same game with matrix models. And since I saw and I have evidence that a phase like this exists in the matrix models, then I have to try to understand what this phase corresponds to. And the idea is the same. So I have to take the Larsen limit with lambda fixed, so the Larsen-Hooft limit. And for high enough energies, I only have one available saddle for my theory, and this is a black zero brane in type 2a. As I go to lower energies, I'm getting a phase transition. I'm going to explain later how this works. And then I have another, again, unstable phase, but this unstable phase now is a small black hole localized along the M theory circle. So it is again a Schwarzschild black hole localized on S1 in this case. And again, as I'm going to even lower energies, I'm expecting to have an 11-dimensional graviton gas. So the difference between these two is that this is happening always in 10 dimensions. But in the case of matrix models are supposed to be a non-perturbative definition of M theory. So the way I explained before how the energies affect the size of the 11th circle, it has an interpretation that as you go to low energies, the 11-dimensional circle opens up. So you are building essentially an 11-dimensional space-time. So you are the circle grows and you are accessing this way the M theory phase. And the idea is that here there is a transition between a 10-dimensional theory and an 11-dimensional theory. So now I want to discuss that there is so this idea here is that, so you see here that T2 goes like n to minus 5/9, and T1 goes like n to positive powers, 1/3. I'm going to explain a while how these T2 and T1 are obtained, but the idea is here that in the large and limit, there's a wide separation between the two phases. And this can be schematically shown as a big overlap between different phases here. So these lines here are not precise. And there is a lot of mixing between the phases at very low temperatures. Okay, so now how do we understand the transition temperatures T1 and T2? Now T2 corresponds to a Gregory-Laflamme transition, and this transition is again, I try to schematically explain it here. When you have a circle S1 and you have a black string wrapping this circle, there is a critical point that can be expressed in terms of temperature or energies, where this string here collapses to a localized black hole on the circle. And this is the so-called Gregory-Laflamme transition. Now you can find this transition for the matrix model, and you find that this scales with inverse powers of n. On the other hand, to obtain T1 corresponds to the minimum deconfinement temperature. Again, deconfinement temperature means that I have black holes. So I want to ask, what is the minimum, the minimal black hole that I can have in my theory? And this corresponds to taking the Schwarzschild black hole in 11 dimensions to have the mass of the Planck mass. And if you do the calculation, you will find out that you get a scaling with positive powers of n. So when I take the large n limit between these two phases, I get a wide separation between the two. And this is shown as a big hysteresis between the two transition points. I want, of course, to point out that this transition here, or this temperature here, is a crude estimate for the moment. But now we are trying to understand a little bit more this phase here to make contact with what we are doing. So let me now try to raise the energies a little bit and go to what is most well known for these models. And for this, there are very interesting examples of Gates gravity duality. And in my opinion, one of the most precise tests of holography, it appeared in this paper here, where there was a comparison between the energies of the matrix model and the energies of the black hole geometries. So, sorry? Yes, the authors are some of my collaborators, is Hanada, Rinaldi, Vranas, and Berkovits. So the idea is that the energies of the matrix model here, they are compared against the energies of the black hole. And this appeared to be reproduced quite effectively. So here the black line, this black line here is a supergravity description. And these points reported here are the large n and continuum points for the matrix models. So you see that so x-axis is temperature and y-axis is the energy. And the idea is that when you flow to low temperatures, the points start to reproduce this black line. And this can be motivated by doing a fit, by doing a fit over these points, and the two fits start to converge to low energies. But the difficulty is that the BFSS model at low temperatures suffers from the so-called flat directions. So you try to simulate the model, and you see at some point when you go to low temperatures, one of the eigenvalues of the matrix to flow to infinity. So this signals an instability of your model, and when this happens, you cannot extract meaningful physics. So that was the reason why the people in the past couldn't go from below this temperature here. But we found a better way to do this and to tackle this problem and to go to even lower temperatures around 0.25. So the idea, again, is, of course, there are many studies in the deconfined phase for the energy and in general, and an incomplete list of people can be found here. And so the idea about, so this expression here concerns the expansion of the energy of the black hole geometry. So this is the term which captures the large n. And when you want to understand finite n corrections, you can include, of course, an expansion of this kind. And I'm showing in blue labels here the coefficients of the terms which can be computed analytically from the gravity side. The rest terms cannot be computed for the moment. So again, this is the Larsen limit classically, and this precise B0 coefficient can be understood by curvature corrections of black hole geometries. So there was also a work by Costa, Greenspan, Penedones, and Sandos, where they used the BMN model and not BFSS. And the BMN model I advertised before that has a mass parameter. So the mass parameter is interesting because it adds a potential, it adds potential terms in your axion. And what it does is to make your model to be more stable in the low energies. So what we observed is that when you include, yes, thank you. So when you include finite mu corrections, so no, when you include mu, simulations become much more stable at low temperatures. So there is a deformation parameter here, and this f mu is a function which is expanded in terms of mu. And if you take mu to be very small, the energy, this one, is very closely related to that one. So what I want to show now is that when I take the Larsen limit, this term here vanishes. And here I'm showing some new results. So the last era of simulations were stopping here, indicated as purple points. And we were able to do some precision measurements from 0.25. And to stress how much negligible the difference is between 0 mu and finite mu, this is captured here because here are the supergravity lines. And these supergravity lines, there are actually two lines. One line is for mu equals 0, reported here in black. And one line is for mu equals 0.5. It is blue here. So you see that using the BMN model, we are able to go to even lower temperatures and discuss the Gates gravity duality better and with more precision. And the deviation at higher energies from the supergravity results can be understood as alpha prime corrections coming from these terms here. So this is ongoing work, and the paper will be out this month. And now we are improving a little bit the statistics here, but it will be out by the end of the month. So now I'm switching for the last 7 minutes or so to the singlet constraint. And the question is if the singlet constraint is important. And this question has been asked by Maldacena and Milekin in a paper in 2018, where they asked this specific question specifically for the matrix models. So they took the partition functions of the Gates model and the ungates, where the difference is that in the ungates model, you turn off the Gates field. And the idea is that the Gates model has a singlet constraint, which is emerging as the equations of motion from the Gates field, and it has this specific form. And the ungates model, it doesn't have such constraint. In the lattice, what we actually do is that we are turning off the Gates field, so we don't have to take it into account. And again, this is motivated by string theory. The idea is that the total Hilbert space can be factorized in the Gates modes, which are singlets, and the non-Gates, which are non-singlets. So the singlet modes, one can think that Gates invariant, the way you are building singlet states is that by taking the trace, And using the cyclicity of the trace, you are forming closed strings. So closed strings are living deep in the bulk, and non-siglets, you don't have to use a trace, and therefore you don't have cyclicity, and they correspond to open strings. And these open strings can go all the way to the bulk, to the boundary. And the question is, if these non-singlet states, which are living on the boundary, if they affect the physics deep in the bulk. And the conjecture is that at very low temperatures, they don't, because the two models are exponentially close to each other. And we can test this for the matrix models. It has been actually tested for BFSS by these people here, and we recently tested that for BMN. And indeed, it turns out to be true in both cases. So here I have the points of the energy, the difference energy between gates and ungates. And here I have inverse temperatures, and there is an exponential decay between the two. And the good thing about BMN model is that at very low temperatures, it has another effective dimensional coupling, which is in terms of 1/μ to the power of cube. So I can do perturbation analysis, even at low temperatures. It is not strongly coupled. And I can compare the perturbation contribution, the perturbative contribution given by this expression here, which is the U1 sector of BMN. And I can compare this with the non-perturbative simulation results, which is given in red here. So this red and blue correspond to the color codes in this diagram. Here, the red point is a 2-parameter fit given by the non-perturbative data, and the blue one is the perturbative data. And you see that for μ = 5, they approach very well to each other. Okay, good. So this brings me to the synopsis of my talk, and the question I want to answer is, what do we learn from what I've said until now? So we learned that, as Robert also said, that these models are interesting test examples for holography, both at high energies, temperatures, also at low temperatures. The thing is that we've seen a stable confined phase, and this was very surprising because it was the first time that we saw something like this. And it seems like an interesting possibility to probe contents of M theory, but for this we need to study better the Schwarzschild black hole. And of course, what about other objects like the membrane or the fibrane? Of course, these are much more difficult questions, but I think hopefully in the future we might get there. And another interesting test example is for the internal energies of the matrix model and the black zero brane geometry. And we can do, nowadays, we can do precision tests, and it seems that we are capturing very well the situation. They are doing large N and continuum extrapolations. Another interesting possibility that we learned is that the gates constraint might not play an important role for the idea of holography. So we might have non-gates gravity understanding or paradigms. And of course, it will be important to understand the idea of stringy corrections in this context. So of course, in the last 2 minutes, I'm not going to get there, but it is important to stress that more studies have to be performed, both for the confined phase, if it exists, but most importantly for the deconfined phase, which might shed some light in the idea of holography, the idea of M theory, and in general, matrix quantum mechanics. So thank you for listening.
Thank you. Okay.
Thank you for bringing this over. I have a very general question on that because I'm not expert on this numerical things. So in this most basic idea, CFT duality conjecture with Super and Mills on the left-hand side.
Yeah.
Well, can you compute anomalous dimensions of some operators? So I mean, what kind of observables you can compute this way?
In which example yours?
Yeah, this idea is S5 versus Super and Mills. So
Yes.
for example, I'm interested in some simple operators on the CFT side and need to know anomalous dimensions. In principle, some of them are known from integrability, but well, okay, numerics can be helpful. So can you compute those?
Numerically, you mean?
Yeah.
Well, the straightforward answer is I don't know, because the model I'm describing here is it doesn't have a CFT counterpart. So it's it has units of the 't Hooft coupling is energy cubed, so it's not a CFT. The observables we are describing here is like observables emanating from the partition function, like energy, the Polyakov loop, and the sum of the scalars squared, and observables like this. It might be possible, but in this context, the answer is I don't know. It's not really obvious to me. And the next thing is that for CFT4, like Super Young-Mills, I don't think there is. I don't think we are there yet to simulate this kind of model. So these models here are toy models if you compare them with D equal CFT4, for example, when you have Super Young-Mills in 4 dimensions. There have been some examples for 1+1, but I don't know for more than that.
Okay, thank you.
Now, okay. Oh. Okay, sorry. I forgot we are multimedia.
Yes, Jun?
Hi. So it's very nice that you found the confined phase from the simulation, and it's interesting to interpret as M theory. But is there any way to identify the 11-dimensional direction from matrix quantum mechanics?
Yes, that's an interesting question, and I cannot really think of an observable that shows the growth of the 11th dimension.
Mm-hmm.
So it's quite difficult to understand this in this kind of level.
Mm-hmm.
The idea that we have in mind is that as you go to lower temperatures or lower energies,
Mm-hmm.
the circle, the 11-dimensional circle, starts opening up.
Mm-hmm.
But at least to me, it's not clear how to find a parameter in matrix model that tells you that something is growing.
Uh-huh.
But an interesting question that we haven't thought of deeply.
Okay. Well, maybe you can calculate the energy versus temperature and compare it with the M theory predictions for the Schwarzschild black holes in M theory, right? So
yes, one interesting example, but the difficulty is that in this case, when you have, so the idea is that when you have a Schwarzschild black hole which is boosted along the 11th circle, and to do thermodynamics there, it's a little bit challenging for the moment. We are thinking about this, and it is a direction that we are trying to pursue now.
I see. Thank you. Very interesting.
Okay. Wait a moment. Okay, now, okay. Now we can thank again the speaker. Okay, little comment. With the organizing committee, we decided that this year Corfu was to be in presence because of the Corfu spirit. So the 3 hours of lunch break are as important as the talks for us, because it's a way to meet people and to mingle, also to go to the beaches. However, we made some exceptions. There are 3 exceptions for our colleagues that are in the extreme Far East, for which still there are some travel restrictions. And therefore, we have two colleagues from Japan, one from China. I'm not saying which China, not to go in trouble. And one instead is Vlado Dobrev, with the last day he had some intervening medical problems. So we made only these exceptions. This is the next talk is one of these extreme Far East expressions, and is Tsuchiya Asato Tsuchiya, and the title is Renormalization Group and cMERA Remote. Asato-san, I will at 10 minutes time discreetly say 10 minutes with this microphone. I hope you will hear me. Actually, okay. We don't see him. Is he there?
Okay. Can you hear me?
Yes.
Can you hear me?
Now.
Okay. Okay. Sorry.
And you think you should share the screen or the
oh,
something?
yes. Okay.
Okay, we can see your screen.
Okay.
So
okay.
I'll tell you 10 minutes and 5 minutes time.
Hi. Yes. Okay, so okay. Oh, okay, first of all, I'd like to thank the organizers for kind invitation to the workshop. This talk is based on a collaboration with Takaaki Kuwahara, Go Tanaka, and Kazushi Yamashiro. Okay, so emergence of space-time is seen in various contexts, such as large induction, matrix models for non-critical strings, and matrix models for superstring theory, which were discussed by previous 2 speakers and will be discussed by several speakers in this conference. And the AD-CFT correspondence or gauge gravity correspondence. Emergent spacetime seems natural in quantum gravity, since the spacetime itself fluctuates in quantum gravity. Here we focus on the AD-CFT correspondence. AD-CFT correspondence is a conjecture that CFT in d+1 dimensions is equivalent to quantum gravity on ADS d+2. And the large N and strong coupling on the field theory side correspond to classical gravity on the gravity side. Here is a metric Poincare coordinates of ADS-T plus 2, you can see that this is invariant under this scale transformation, which allows us to interpret Z, coordinate Z as a scale for renormalization group. Namely, large Z correspond to IR and small z correspond to UV. This spacetime has a boundary at z equal to 0, and roughly the field theory lives on the boundary. More precisely, we introduce the UV cutoff epsilon, which is interpreted as lattice spacing, and then the field theory lives on the hypersurface specified by z equal to epsilon. Then now in ADS-CFT, bulk geometry emerges from the degrees of freedom of quantum field theory. Then we would like to ask, can we derive quantum gravity directly from the degrees of freedom of quantum field theory? Then now quantum entanglement is expected to give an answer or hint to this question. Here is a definition of so-called entanglement entropy. We divide the space in field theory into two parts, A and its complement B. Then the total Hilbert space is decomposed as a tensor product, HA and HB. Then the reduced density matrix is defined by taking the trace, partial trace over HB of total density matrix. Then the von Neumann, the entanglement entropy for the region A is given by the von Neumann entropy for rho A. So the entanglement entropy in quantum field theory has the following behavior, where D is the space dimensionality. For D larger than 2 or equal to 2, it's proportional to the area of the boundary of the region A over divided by epsilon to D minus 1, where epsilon is the UV cutoff. For D equal to 1, it is given by C over 3 times log L, where C is the central charge and L is the length of the region A. Now the U-Takayama formula connects the quantum entanglement entropy to the geometry through this equality, where SA is the entanglement entropy for the region A in CFT on the boundary, and gamma A is the surface in the bulk whose boundary agrees with the boundary of the region A. And the numerator is the minimum of the area of such bulk surface, and the Gn is Newton constant. Okay, so this formula suggests that understanding the relationship between emergence of space-time and quantum entanglement allows us to gain insights into the construction of quantum gravity. In particular, the cMERA, which is a continuum counterpart of the MERA, is expected to realize the emergence of space-time through quantum entanglement. While cMERA is obtained successfully based on the variational method in free field theory, it is quite non-trivial to construct in interacting field theory. which is relevant in the context of ADS-CFT correspondence because strong coupling regime correspond to classical gravity on the gravity side. So now here we propose an approach based on the renormalization group to the cMERA in interacting field cell. Okay, so this is the plan of the present talk. Now, in the next section, we review the cMERA and MERA and cMERA and their connection to the ADS-CFT correspondence. And in section 3, we explain our approach to cMERA based on the renormalization group. And in section 4, we consider the perturbation theory. And in section 5, we discuss the non-perturbative cMERA. And in section 6, we conclude and discuss. Okay, so before going to MERA and cMERA, let me start with matrix product state. Generally, by using tensor network, we can efficiently construct a trial wave function in quantum system. As an example, let us consider a spin chain consisting of n spins in one dimension. The general wave function takes this form. You can see that the degrees of freedom of this wave function is s to n, where s is the magnitude of spin. Now we introduce matrix product state for this wave function, which takes this form, where m alpha beta I of sigma is a chi by chi matrix, which depends on spin and the position of spin. And it's represented by this diagram. So you can see that this has degrees of freedom of n times s times chi square, which is much less than this one. So actually, you can determine this tensor by using the variational method. The matrix product state is represented by this figure. Now, let us consider the region A in the spin chain and estimate the entanglement entropy in matrix product state. Here, gamma A is a curve or path connecting two ends of A, and the number of bonds of gamma A is a number of bonds crossed by gamma A. In this case, this is just 2. Chi is called the bond dimension. Now, bond represents correlation between tensors. So each bond contribute to entanglement entropy at most by log chi. So we have this bound for the entanglement entropy for the region A, namely minimum of the number of bonds of gamma A times log chi. And as I said, this is equal to 2 in this case. So we have a bound for SA 2 times log chi. Now let us recall the entanglement entropy in quantum critical system in one dimension, which is given by this one. So this means that the matrix product state does not reproduce entanglement entropy in quantum critical system in one dimension. So now next, let us consider the tree structure tensor network, TTN. For example, let us consider a spin chain consisting of 4 spins in one dimension. Now the wave function takes this form. We introduce the tensor T and W1 and W2 here. And they are called isometry. And they merge two spins into one spin, as you see in this figure. And okay, now these tensors are determined by variational method. Now, so now we have a layers here, then we parameterize these layers by U. U there equal to 0, -1, -2, and so on. So if these layers are regarded as scale, TTN looks like renormalization group in real space, but not exactly, renormalization group. So we remark that the correlation between spin 2 and spin 3 is not taken into account in this setup. So now this causes a problem. In this case, we consider the region A here again, and draw gamma A like this. Then minimum of bonds, number of bonds of gamma A is again equal to 2. So the entanglement, so the SA has this bound again. So which means that TTN does not reproduce entanglement entropy in quantum critical system in one dimension. So now we get to MERA, which represents multi-scale entanglement renormalization ansatz. So as an example, let us consider a spin chain consisting of 4 spins in 1D. Now the wave function takes this form. We introduce the tensor U, which can be regarded as unitary matrix, and U is inserted as in this figure. So now this tensor creates or erase correlation between nearest neighbor spins. Actually, if you look at this figure from top to down, this tensor creates correlation. So in this case, this is called entangler. On the other hand, if you look at this figure from down to top, these tensors erase correlation between nearest neighbor spins. So in this case, this is called disentangler. In the following, we recall this tensor entangler. Now, isometry and entangler are determined by variational method. So now let us consider again the subregion A in the spin chain here. In this case, gamma A is drawn like this. So now the minimum, the bonds of gamma A, minimum of bonds of gamma A is equal to 2 times log L, because the height of this tensor network is given by log L. So the SA has this bound in this case. So if this inequality is saturated, this reproduces the behavior of the entanglement entropy in quantum critical system in one dimension. So motivated by this fact and due to Carnegie formula, we regard the number of bonds of gamma A as discrete lengths. Namely, we introduce the metric which takes this form, where epsilon is lattice spacing. U is a parameter specifying layer. So if we make a change of variables, g equal to epsilon e to minus u, then this metric reduces to this one, which is nothing but the ADS2 metric, which is a constant time slice of ADS3. So now we are regarding this tensor network as discretized ADS2. So in this counting, you can see that the introduction of this entangler is important. So more precisely, quantum critical system has scale invariance. So entangler, in this case, entangler U are constant. So we can consider this type of metric. More generally, in non-critical system, tensor U should depend on the scale U. So we should consider the metric like this, where GUU represents the strength of entanglement at the scale U. So okay, so now taking the continuum limit of the tensor network is quite non-trivial. So we would like to start with continuum version of cMERA from the beginning, namely continuum cMERA, which is called cMERA, should be important for extracting geometry from the network. So cMERA is constructed as follows. The psi 0 is the ground state. This is a trial function of the ground state at UV, which is obtained by acting some unitary operator on the ground state at IR, which satisfies this relation. Where L hat is the dilatation operator, which generates this transformation. And the unitary operator is assumed to take this form, where K hat is a continuum analog of entangler, and L hat is a dilatation operator, which is analog of the isometry. Actually, in free field theory, this entangler can be determined by the variational method in such a way that psi 0 indeed agree with the ground state. So now we introduce quantum information metric. The Hilbert-Schmidt distance between two density matrices given by this formula, and if the density matrix has a continuous parameter lambda, quantum information metric is defined by this equality. For two pure states, Hilbert-Schmidt distance is given by this equation, and quantum information metric is given here. So now we introduce quantum information metric in cMERA like this. So we subtract the contribution of dilatation in order to extract only contribution of entangler. Actually, the information metric is represented by the entangler in this case, and this metric should measure local quantum entanglement, and it should be related to geometry at U. So there is a conjecture that actually this information metric is proportional to the metric in the bulk GUU. Now, in free field theory, it is obtained as follows. And if we take the limit, massless limit, it reduces to the constant. Actually, this corresponds to ADS metric. Furthermore, in the case where the region A is half space specified by this inequality, by calculating entanglement entropy based on the ground state function, wave function, and comparing the result with the Ryu-Takayanagi formula, one obtains actually this relation. However, this is an observation for free field, where free field theory, where the Ryu-Takayanagi formula is not applicable. Indeed, classical geometry corresponds to the strong coupling regime in field theory. Thus, it is important to find the entangler in interacting field theory. So now, okay, so let me explain our approach to CFT based on renormalization group. First of all, how to assume K hat in variational method for interacting field theory is not clear. So here we construct cMERA based on RG rather than variational method. There are some previous studies. Actually, VA for interacting scalar field theory has been studied by these people. We make a comment later about this. And RG approach to cMERA has been studied for ON vector free field theory by these people and for interacting scalar field theory by these people. And their results seems to be different from ours, and our method is much simpler than theirs. So now this is our approach to cMERA based on RG. The first step is that we obtain the ground state at scale U, psi 0 of U based on RG. And the step 2 is by calculating the derivative of psi 0 with respect to U, we can obtain the entangler K hat by using this equation, which comes from the definition of cMERA. Now, as for RG, we consider two methods. The one is perturbation theory. Actually, we make a perturbative expansion in order to gain insight into non-perturbative cMERA. For instance, in order to know what type of terms appear generally. And the second is a non-perturbative method based on exact renormalization group, or a functional renormalization group. Okay, so now so let me discuss perturbation theory. So let us recall the equation for cMERA, where x is x equal to minus I k plus L. This is an anti-Hermitian operator. And we make a perturbative expansion for ground states like this. Alpha is a expansion parameter. And we obtain psi 0, 0 and psi 0, 1 iteratively. And we also expand this operator in alpha, then the equation, zeroth order in alpha of this equation takes this form, and the first order in alpha takes this form. So the left-hand side can be obtained by taking the derivative, and you can obtain x0 by using this equation and substitute the result into this equation, and you can obtain x1. So you can obtain x in this way, order by order. And for concreteness, let me consider the d plus one dimensional free scalar field theory. The Lagrangian is here, and we introduce effective cutoff lambda by introducing the cutoff function k, which behaves as follows. Namely, for p square less than lambda square, it is almost constant, and when p square is larger than lambda, it rapidly dumps like this. So now we introduce this notation. And canonical conjugate momenta and canonical commutation relation are given here. And Hamiltonian is calculated as follows. And we make a rescaling like this. And the rescaling Hamiltonian takes this form, where we introduce the bare cutoff lambda 0 and the scale parameter u here. So UV limit corresponds to u equal to 0, and IR limit is u equal to -1. U is a continuum analog of parameter in the cMERA, discrete parameter in cMERA. So now we introduce notation KP, which is given by this, and omega p is here. So you see that the U dependence appears only here in free field theory. So now creation and annihilation operators are given here, and they satisfy this commutation relation, and Hamiltonian is represented in terms of these operators as follows. Where V is volume of space, and there is no cutoff dependence here as we expected. Now vacuum is ground state is characterized by this equation, and in particle state is given by is obtained by acting creation operators like this on the ground state. So this state is energy eigenstate, and the energy eigenvalue is here. So this is this corresponds to vacuum energy, and there is again no cutoff dependence in energy eigenvalue. So now we introduce eigenstate of phi hat, which it's defined by this equation, and the wave functional for vacuum is defined by this equation, and this functional satisfies the functional differential equation like this, which comes from this condition. And you can solve this equation explicitly. The result is here, and this term is comes from the normalization condition of the wave functional. So now let us move on to the interacting case. the Hamiltonian is given by free part and interaction part. Alpha is a expansion parameter, and H0 is a free part as before, and H into is the interaction part. The first term is mass counter term, and the second term is lambda phi to the fourth interaction. Now we consider the perturbative expansion for ground state and energy like this, up to order alpha square here. So the now the first order in alpha is obtained by using this formula, and we obtain this result. So now Kp and omega p are defined here. So now the wave functional, you can obtain wave functional through path integral. This is a path integral representation of ground state. We consider the Euclidean theory and consider the path integral over Euclidean time minus t from minus t to 0. And we take the t go to infinity limit, and we impose this condition on the boundary tau equal 0, tau equal to 0. Now the value of the field is fixed by this value at tau equal 0. Now by taking t go to the infinity limit, we can extract only the ground state like this. Now Lagrangian takes this form, and L0 and L0 is a free part and L into is a interaction part. Now, in order to calculate this path integral, we expand the field around the classical solution in L0, and so actually phi c is the classical solution in.
You have 10 minutes.
Sorry?
You have 10 minutes.
10 minutes. Okay, thank you. Now, okay, phi c is the classical solution and chi is the quantum fluctuation. We impose a boundary condition at tau equal 0. Phi c is equal to actually this value, and chi is 0 at tau equal 0. And classical solution is given explicitly here, and chi is fully expanded. Chi has a fully expansion like this, and the propagator for chi is given here. Okay, so by using this setup, we can calculate the wave functional for ground states. We parameterize functional like e to I times phi 0, 0. And we expand I in terms of alpha like this. Then I1 is given by these diagrams. The results agree with the results obtained in canonical formulation. And I2 given by these diagrams, these are results. Now we can obtain the x0, which is k minus I times k tas L. We take the derivative with respect to u, then the result is here, and we rewrite this expression by using creation and annihilation operator, and finally we obtain this one. And by using this relation, we obtain the X, zeroth order X here. We added this term in order to make this operator anti-Hermitian, and the final result is here. This is phi pi plus pi phi term. Now, in a similar way, we can obtain the X1 like this. This is the anti-Hermitian operator, and we have a phi pi and pi phi term here. And we remark that this type of term does not exist in the answer used in the variational method by these people. This is a flow equation for the counter term for mass term. Now, okay, so finally, let us discuss the non-perturbative cMERA. So in the spirit of the exact RG or functional RG, we can derive a non-perturbative functional differential equation for the ground state wave functional. We start with the expression for the ground state by path integral, and by using this condition, which means that norm of this state does not depend on the scale U, then we can obtain the differential equation, functional differential equation for psi 0, which takes this form. So now we confirmed that the vacuum wave functional that we obtain perturbatively satisfies this equation to the first order. We are now examining the second order. So we expect to find non-perturbative entangler by solving this equation non-perturbatively. And so we can actually infer from perturbative results what type of terms appear in the solution. Okay, so let me conclude. So we propose the method which is based on renormalization group to construct cMERA in interacting field theory, which is relevant important in the AD context of AD-CFT correspondence. The important equations are summarized here, and our strategy is to first obtain wave functional depending on U based on RG, and determine K hat by using this equation. So now we construct cMERA perturbatively to gain insight into non-perturbative cMERA. For instance, what type of terms appear generally in the entangler. Our entangler includes a type of terms that are not included in the trial answers for K hat in VA used by these authors. And we also discussed the non-perturbative method based on the exact RG. So the outlook is here. We would like to calculate entanglement entropy and find the relationship between entangler and geometry in the interacting field theory, hopefully in the non-perturbative cMERA. For that purpose, we need to develop non-perturbative cMERA further. Now, finally, we would like to consider the extension to gauge field theory. Thank you for your listening.
Thank you very much. Okay, are there local questions? Yes, one there.
Thank you. It's a bit non-local question because it's about entanglement. So, for example, if we take three-dimensional free scalar field, then entanglement entropy across circle is some funny number proportional to log 2 plus zeta 3 over some pi squared. So with your new technique, can you reproduce something like that?
Okay. Yeah, yes, yes. In the conformal limit, we can reproduce. Okay. So in free field case, we can reproduce such behavior, but we are examining the interacting case now. So yeah.
Okay, it can be interacting as well. You can take Ising model, and then again in the large n limit, it's some funny number. So can you reproduce that?
Yeah. So yes. Yes. We expect the. We expect to. We can expect. We expect that we can take the large n limit in the interacting cell. So, yeah, we expect the result proportional to the central charge.
Thank you.
Okay. Are there Corfu questions or yeah, or non-Corfu questions, non-local, but I was taught that local and non-local has a different meaning. Please, Yun-san.
Yes. Okay, thank you. So I thought that you were trying to examine the correspondence to the ADS geometry that you talked about in the introduction. But in the case of interacting theory, do you expect the same conclusion to hold, or do you expect something else?
We expect the same conclusion. Yeah. So for example, yeah, if we can find the fixed point of this equation, we obtain the conformal field theory, non-perturbable. Then we can calculate the entangler and information metric. Then we eventually we expect to obtain ADS metric.
And from your results at the perturbative level, can you confirm it already, or?
So if we take the massless limit, we can obtain the information metric, a constant information metric. So that corresponds to ADS metric. So in that sense, we obtain ADS space-time. I think we have to consider the strong coupling regime. So we eventually consider this type of analysis. So. Okay.
So that is
this is the first step to such.
Yeah. Okay. Yeah, I understand. Yeah. Okay. Thank you.
Okay, I don't see hands raised, neither virtual nor real. And George has a small announcement. I have an announcement.
Concerning lances and so on, there are the following possibilities. Most of us will go to Two Brothers, which is in the Garitsa Bay Gulf. And this on your way as you go to the airport or something is the second, let's say, stop. is near the sea, so you can see two brothers. Of course, there are several others that you can visit, and there is also a possibility that we have here with €6 that you can ask for a lunch basket for those who would like to work a little bit more here or go to the beach. It's a little bit late, so I would like to ask the chair to be more on time, because we have the possibility up to the coffee break to order. But anyway, let's try. There is a list, so just go, please, in case you are interested for a lunch basket, and sign now.
Okay, you sign now. Then there is the coffee break. I suggest we try to make a compromise, and we meet again at 12:10. Okay, please, all the speakers send a slide to the corfusion@gmail.com. And I have an announcement for good news for Italians and Neapolitans in particular. San Gennaro ha fatto il miracolo. Those that don't know this will not care.